Welcome to Sleepy Science Stories. I'm so glad you're here. Before we begin, I'm curious, where are you watching this from? And what time is it where you are? Whether you're tucked in bed as the day winds down, or perhaps it's the middle of the night and sleep eludes you, you're exactly where you need to be. Tonight's journey will take us through the gentle realm of science and wonder. No rushing, no urgency, just a slow, peaceful exploration designed to ease your mind and guide you toward rest. So find your most comfortable position. Let your body sink into wherever you're resting. Take a slow, deep breath and another. Tonight, we explore one of nature's most spectacular displays, lightning. That brilliant flash that splits the sky, illuminating clouds from within and casting shadows across the landscape in an instant. But rather than focusing on the drama of the storm, we'll take our time understanding the gentle, invisible processes that build toward that moment. We'll begin with something as simple as a water droplet and follow its journey through the atmosphere, watching as physics transforms it into something extraordinary. Imagine yourself standing in an open field on a summer afternoon. The sky above stretches endlessly, painted in shades of blue that deepen toward the horizon. Clouds drift by, their forms constantly shifting, merging, separating again. They appear solid from below, these massive structures floating overhead, but you know they're made of something as insubstantial as mist. Billions upon billions of tiny water droplets, each one so small that it takes a microscope to see it clearly, suspended in air. These clouds are not still, though they might seem that way from the ground. Within them, currents of air rise and fall, carrying water droplets up into colder regions of the atmosphere, then letting them descend again. It's a complex dance, this movement within clouds, driven by temperature differences and the uneven heating of the Earth's surface below. Some clouds remain thin and wispy, mere suggestions of moisture in the sky. Others grow tall and massive, building into towering structures that can reach heights of 10 or 12 miles. The clouds that create lightning are these tall ones, the ones meteorologists call cumulonimbus. The name itself is beautiful in a way. Cumulus meaning heap or pile in Latin, nimbus meaning rain cloud, a pile of rain cloud stacked high into the atmosphere. If you were to see one from the side, from an airplane window perhaps, you'd notice its distinctive anvil shape at the top, where the rising air finally hits a boundary it cannot cross and spreads outward instead. But we're getting ahead of ourselves. To truly understand lightning, we need to start smaller, much smaller. We need to understand water itself, that remarkable molecule that covers most of our planet and makes up most of our bodies. Two hydrogen atoms bonded to one oxygen atom, forming a shape that's slightly bent, like a very shallow V. This simple structure, H2O, has a quirk that makes everything else possible. The oxygen atom in water pulls electrons toward itself more strongly than the hydrogen atoms do. Scientists call this electronegativity, this tendency of atoms to attract electrons. Because oxygen is more electronegative than hydrogen, the electrons in water molecules spend more time near the oxygen atom than near the hydrogen atoms. This creates what we call a polar molecule. One end has a slight negative charge, while the other end has a slight positive charge. You might wonder why this matters. Perhaps you're starting to feel your thoughts slow down, your breathing deepen. That's exactly right. Let the science wash over you gently. This polarity of water molecules is the foundation of everything that follows. It's why water droplets in clouds can become charged with static electricity. It's why ice crystals can strip electrons from other particles. It's the reason that simple H2O, abundant and familiar, can participate in the creation of one of nature's most powerful phenomena. In the atmosphere, water exists in three forms simultaneously. There's water vapor, the invisible gas that evaporates from oceans and lakes and leaves of plants. There are liquid droplets, the tiny spheres that make up most clouds. And there are ice crystals, forming in the coldest parts of high clouds, taking on intricate geometric shapes as water molecules lock into solid crystalline structures. The air around you right now contains water vapor, even if you can't see it. In humid climates, there might be enough moisture in the air that you can feel it on your skin, that sense of heaviness or dampness. In dry climates, the water vapor is still there, just less of it. This invisible water is always moving, always cycling between Earth's surface and the atmosphere above. When the sun heats the ground, the air directly above it warms as well. Warm air is less dense than cool air, so it rises, creating vertical currents called convection. As this warm air rises, it carries water vapor with it. Higher in the atmosphere, where the air is cooler, some of that water vapor condenses into liquid droplets. This is how clouds form. Warm, moist air rising and cooling, its water vapor transforming into something visible. On some days, this process remains gentle and limited. Small clouds form and dissipate, their lifespans measured in minutes or hours. The rising air doesn't have enough energy to build truly tall clouds. Perhaps there isn't enough moisture. Or perhaps the atmosphere is too stable, with warm air lying above cool air instead of the other way around. Whatever the reason, these small clouds come and go, sometimes casting shadows that drift across the landscape, sometimes releasing light rain that evaporates before it reaches the ground. But on other days, conditions align differently. The ground heats intensely, perhaps after several days of building heat. Moisture is abundant, maybe from a nearby ocean or gulf, maybe from recent rain that's now evaporating back into the air. The atmosphere is unstable, with cool air lying above warm air, ready to flip. These are the days when storms build. The first sign might be a single puffy cloud, growing taller as you watch. It starts as a small cumulus cloud, the kind you might see on any summer day. But this one doesn't stop growing. Fed by powerful updrafts of warm, moist air, it continues to build vertically, climbing higher and higher into the sky. Within that growing cloud, water droplets are being carried upward at speeds that might surprise you, sometimes 10 or 20 or even 30 meters per second. That's faster than you could sprint on level ground. As droplets rise within this growing cloud, they enter progressively colder regions of the atmosphere. Temperature in Earth's atmosphere generally decreases with altitude, dropping about 6.5 degrees Celsius for every 1,000 meters of elevation. At the base of the cloud, temperatures might be comfortable, perhaps 20 or 25 degrees Celsius. But at the top of a tall thunderstorm cloud, temperatures can plunge to minus 40 or 50 degrees Celsius. Somewhere in the middle of the cloud, usually around 5 or 6 kilometers above the ground, the temperature drops below freezing, 0 degrees Celsius, the point where water becomes ice. You might think that all the water droplets would freeze at this altitude, but they don't. Some do, yes, creating ice crystals, but others remain liquid. Even though they're well below the freezing point, scientists call these supercooled water droplets, and they're surprisingly common in clouds. Pure water, free of impurities, can remain liquid even at temperatures well below 0 Celsius. It needs something to freeze onto: a tiny particle of dust, a grain of pollen, a fragment of sea salt. These particles are called ice nuclei, and they provide a surface where ice crystals can begin to form. Without them, water can supercool, remaining liquid at -10 or -20 or even -30 degrees Celsius. In the developing storm cloud, both exist together, ice crystals and supercooled droplets, occupying the same space, being carried upward by the same powerful updrafts. This coexistence is crucial. The interaction between ice and supercooled water is at the heart of how lightning forms. But we're not there yet. There's more to understand first, more pieces of the puzzle to put in place. Let your breathing slow. Feel yourself sinking deeper into comfort. The science will continue, unfolding at its own measured pace, layer upon layer of understanding building toward that brilliant flash. But for now, we're still in the middle stages, watching the cloud grow, seeing ice begin to form, observing the dance of particles too small to see with the naked eye. The cloud continues to build. More warm, moist air feeds into it from below, drawn toward the growing storm like fuel feeding a fire. The updrafts strengthen, becoming more vigorous. The cloud's top pushes higher, breaking through 10 kilometers, then 11, then 12. At these heights, the air is thin and desperately cold. The water vapor here freezes almost instantly, creating a layer of ice crystals at the cloud's peak. These crystals spread outward, unable to rise any higher, forming that characteristic anvil shape. From a distance, the storm cloud now looks like a massive mushroom with a tall vertical shaft and a broad, flat top. It's beautiful in its way. This structure, built entirely of water in its various forms, held aloft by nothing but rising air. And within it, invisible to any observer, the conditions for lightning are beginning to form. Chapter 2: Water's Journey from Ground to Sky. To truly understand what happens inside a thunderstorm, it helps to follow a single water molecule on its journey from the ground to the heights where lightning forms. This particular molecule, let's call it ours, though it's indistinguishable from countless billions of others, starts its journey in the ocean. The ocean is vast beyond easy comprehension. It covers more than 70% of Earth's surface, containing roughly 1.4 billion cubic kilometers of water. That's billion with a B. Try to picture that much water, and the mind simply can't hold it. Our molecule has been in this ocean for perhaps millions of years, cycling through currents, being absorbed by phytoplankton and released again, sinking to the depths and rising back to the surface. On this particular summer day, our molecule finds itself near the surface, in the top few centimeters where sunlight penetrates most strongly. The sun's energy, traveling 93 million miles through space, warms the ocean's surface. This warmth increases the kinetic energy of water molecules, making them vibrate and move more quickly. Some of them, including ours, gain enough energy to break free from the liquid water entirely, transforming into water vapor, a gas. This process, evaporation, happens constantly across all of Earth's oceans, lakes, rivers, and even moist soil. It's part of the water cycle you may have learned about in school, though perhaps without truly appreciating its scale. Every day, approximately 1 trillion tons of water evaporates into the atmosphere. That's roughly the weight of 10,000 aircraft carriers, lifting invisibly into the sky. Our water molecule, now a gas, rises with the warm air above the ocean. It's carried by wind, drifting across the water's surface, mixing with billions of other water vapor molecules. If you could see water vapor, the air would appear thick with it, but it remains invisible to our eyes. Only when it condenses into liquid droplets or ice crystals does water become visible again. The air carrying our molecule moves inland, pushed by prevailing winds. It crosses the coastline, moving over land where the sun has been heating the ground all morning. The land heats more quickly than the ocean. This is because soil and rock have lower specific heat capacities than water, meaning they warm up faster for the same amount of solar energy. By early afternoon, the ground temperature has climbed well above the air temperature. This creates exactly the conditions needed for convection. The air directly above the hot ground warms, becomes less dense than the cooler air above it, and begins to rise. Our water molecule, still in vapor form, rises with this air. It's a gentle ascent at first, just a few meters per second, but as the warm air continues to rise, it accelerates. As our molecule climbs higher, it enters air that's progressively cooler. This cooling happens because air expands as it rises into regions of lower atmospheric pressure, and expansion causes cooling, a principle of thermodynamics that you don't need to remember the details of. Just know that rising air cools. For every 1,000 meters of altitude gained, the air temperature drops by about 6.5 degrees Celsius. At some point during this ascent, perhaps at 2,000 meters, perhaps at 3,000, depending on the day's conditions, the air becomes cool enough that our water molecule can no longer remain as vapor. The process of condensation begins. But condensation, like freezing, needs a surface to occur on. Our molecule drifts until it encounters a tiny particle, perhaps a speck of dust that was lifted into the atmosphere from a desert thousands of kilometers away, or a particle of sea salt from ocean spray, or even a tiny crystal of sulfate from volcanic emissions. Whatever the particle is, it serves as a condensation nucleus. Our water molecule, along with thousands of others, condenses onto this tiny speck, forming a microscopic water droplet. This droplet is perhaps 10 or 20 micrometers in diameter, far too small to fall as rain. In fact, it's so small and light that even the gentlest upward air current can keep it suspended. This is the beginning of a cloud. All around our droplet, the same process is occurring. Water vapor condensing onto countless particles, each forming a tiny droplet. Millions and millions of droplets, each 1 minute, together creating something visible. A cloud. From the ground, someone looking up might notice this cloud beginning to form, a small patch of white appearing in the blue sky. But our droplet's journey is far from over. It's caught in a strengthening updraft, part of a developing thunderstorm. The warm air continues to rush upward, carrying our droplet with it. As it rises, it may collide with other droplets, merging with them to form a larger drop. This process, called coalescence, happens constantly in clouds. Droplets bump into each other, stick together, grow bigger. However, In the powerful updrafts of a developing thunderstorm, something else is happening too. The rising air is so strong that even relatively large droplets can't fall out of it. Instead, they're carried higher and higher into ever colder regions of the cloud. Our droplet, which started its cloud existence in air that was perhaps 15 degrees Celsius, now finds itself in air that's 0 degrees, then -5, then -10. Here's where things become interesting. Our droplet is now supercooled. It's liquid water at temperatures well below freezing. This is an unstable state. The water molecules in the droplet are moving slowly in the cold, but they haven't arranged themselves into the crystalline structure of ice. They're waiting, in a sense, for something to trigger the transition. That trigger comes when our droplet collides with an ice nucleus, perhaps a tiny ice crystal that has formed elsewhere in the cloud, perhaps a particle of dust that has special properties conducive to ice formation. The moment of contact is almost instantaneous. The water molecules suddenly arrange themselves into the hexagonal crystalline structure of ice, and our droplet becomes an ice crystal. This transformation releases a tiny amount of heat, the latent heat of freezing, which slightly warms the surrounding air. Multiply this by billions of droplets all freezing at various times throughout the cloud, and you can see why thunderstorms are such powerful engines of heat redistribution. They take warm, moist air from near the surface and transport it high into the atmosphere, releasing enormous amounts of energy in the process. Our ice crystal is no longer just a frozen droplet, though. In the cold, high reaches of the cloud, it begins to grow through a different process called deposition. Water vapor, molecules in the air freeze directly onto the ice crystal's surface, adding to its mass without going through a liquid phase. The crystal takes on a more complex structure, perhaps becoming a dendrite with 6 arms radiating from a central point, perhaps becoming a needle or a column, depending on the exact temperature and humidity conditions. The crystal grows larger, its intricate geometry a testament to the precise way water molecules bond to each other in their frozen state. No two snowflakes are identical, they say. And while that's not strictly true at the molecular level, it's true enough. The conditions that any growing ice crystal experiences are unique to that crystal, and they leave their mark on its final form. But our crystal isn't falling yet. The updrafts in this developing storm are powerful, sometimes exceeding 30 or 40 meters per second. That's more than 70 miles per hour. Winds strong enough to lift not just tiny droplets, but ice particles the size of small pebbles. Our crystal, still relatively small, is carried upward relentlessly, circulating within the cloud. Sometimes it descends slightly, entering warmer air where it might partially melt, its surface becoming liquid, while its core remains ice. Then, the updraft catches it again, carrying it back up into the frozen zone. This cycling between warm and cold regions causes some particles to develop layers of ice, like an onion. These are the beginning stages of hail formation. Though not all particles will become hail, many remain smaller, continuing to circulate in the cloud. Around our crystal, the storm continues to develop. More warm, moist air feeds in from below. The cloud grows taller still, its top now reaching into the stratosphere, that stable layer of atmosphere where temperature actually increases with altitude. This is as high as the cloud can grow. The stable stratosphere acts like a lid, and the rising air spreads outward instead, forming that massive anvil top. Within the cloud, there are now millions upon millions of particles, water droplets in the warmer lower regions, supercooled droplets in the middle regions, and ice crystals and particles in the upper regions. They're all moving, carried by complex air currents that rise in some areas and descend in others. It's a dynamic, chaotic system, but one governed by well-understood physical laws. And it's in this chaos, in this mixing and collision of ice and water, that the conditions for lightning are being created. Our ice crystal is about to play its part in one of the most spectacular energy releases in nature. But the stage is still being set. The actors are still taking their positions. The physics hasn't yet built to its crescendo. You might notice your thoughts drifting, your awareness of the pillow beneath your head becoming more pronounced. That's good. Let yourself sink deeper. The science will continue, gentle and persistent, building understanding layer by layer. There's no rush. The storm cloud isn't going anywhere, and neither are we. Chapter 3. The birth of a storm cloud. A thunderstorm doesn't simply appear. It grows from small beginnings, following a progression that meteorologists can predict with reasonable accuracy. What starts as a small cumulus cloud on a summer afternoon can, under the right conditions, transform into a towering thunderstorm capable of producing lightning, heavy rain, strong winds, and sometimes hail or tornadoes. The life cycle of a thunderstorm has 3 distinct stages: the developing stage, the mature stage, and the dissipating stage. Understanding these stages helps us see how lightning-producing clouds are not static structures, but dynamic systems that evolve over time. Each stage has its own characteristics, its own patterns of air movement, its own personality, if you'll allow a cloud to have such a thing. The developing stage begins with that small cumulus cloud we mentioned earlier. At this point, the cloud is dominated entirely by updrafts, rising columns of warm, moist air. There are no downdrafts yet, no rain falling. The cloud is building, accumulating mass, drawing energy from the warm surface below. It's growing taller, minute by minute. And if conditions are right, it will continue to grow for 20 or 30 or even 40 minutes. During this stage, the cloud transforms from a small, innocuous puff into something more substantial. Meteorologists watch for certain signs that indicate a cloud is developing into a thunderstorm. One of these signs is the rate of vertical growth. An ordinary cumulus cloud might grow slowly or not at all. But a cloud that's becoming a thunderstorm shows rapid vertical development, sometimes adding several hundred meters of height in just a few minutes. Another sign is the development of a sharp, crisp outline. The updrafts in a developing thunderstorm are strong enough to carry water droplets and ice crystals high into the atmosphere very quickly, faster than they can evaporate or sublimate. This creates well-defined cloud edges rather than the soft, fuzzy boundaries of gentler clouds. From the ground, watching through time-lapse photography, you would see the cloud's top bubbling upward like a pot of water coming to a boil. Inside this growing cloud, water droplets and ice particles are being lofted upward at impressive speeds. Some particles make multiple trips through the cloud, caught in updraft regions that carry them to the top, then drift into adjacent areas where they descend slightly, only to be caught by another updraft and carried aloft again. This cycling process is important for 2 reasons. First, it allows particles to grow larger. Each time a water droplet cycles through different parts of the cloud, it has opportunities to collide and merge with other droplets. Each time an ice crystal cycles through regions of varying temperature and humidity, it grows through deposition of water vapor onto its surface, or by collecting supercooled droplets that freeze on contact. Second, and crucially for lightning formation, this cycling creates opportunities for particles to collide with each other in ways that transfer electric charge. But we're getting ahead of ourselves again. First, we need to watch this cloud reach maturity. The transition from developing stage to mature stage happens when precipitation begins to fall from the cloud. Until this point, all the water and ice created in the cloud has been held aloft by the updrafts. But eventually, some particles grow large enough and heavy enough that even the powerful updrafts can't keep them suspended. They begin to fall. As these particles fall, they drag air downward with them. This creates downdrafts alongside the updrafts that still feed the storm. The mature stage of a thunderstorm is characterized by the coexistence of strong updrafts and strong downdrafts, often right next to each other within the same cloud system. This is when the storm is at its most powerful, when the contrast between rising and sinking air is greatest, when the most energy is being released. It's also when lightning begins. The conditions that create lightning, which we'll explore in detail in coming chapters, require the presence of both updrafts and precipitation. The mature stage, with its complex internal structure and powerful air currents, provides exactly these conditions. From the ground, the visual signs of a mature thunderstorm are unmistakable. The cloud has grown into a massive structure, its top flattened into that characteristic anvil shape. The base of the cloud has become dark, sometimes taking on an ominous greenish or bluish tint as light scatters through the dense concentration of water and ice. Rain begins to fall, often suddenly and heavily. Wind increases, sometimes shifting direction abruptly as the downdraft reaches the ground and spreads outward. And then, if you're watching, you might see it, the first flash of lightning. It might be within the cloud, illuminating it from within like a lamp being switched on and off. Or it might extend from cloud to ground, a brilliant, jagged channel of light connecting sky and earth for a fraction of a second. The thunder follows, rumbling or cracking depending on your distance from the flash. This mature stage can last for an hour or more, especially in conditions where the storm can continuously draw in fresh, warm, moist air from below. Some storms organize themselves in ways that prolong this stage even further. Supercell thunderstorms, for instance, have a rotating updraft that can persist for several hours, continuously producing lightning, heavy rain, and sometimes tornadoes. But all storms eventually exhaust their energy source. The downdrafts that bring rain and cool air to the ground begin to spread out, cutting off the supply of warm, moist air feeding into the updrafts. Without this fuel, the updrafts weaken. Less water vapor rises into the cloud, so less condensation and freezing occurs. The energy that powered the storm begins to dissipate. This marks the beginning of the dissipating stage. The storm is dying, though it may take another hour or more to completely fade away. The downdrafts now dominate the cloud structure. The anvil top begins to lose its sharp definition, becoming more fibrous and spread out. Rain continues to fall, but becomes lighter and more intermittent. Lightning becomes less frequent and eventually stops altogether. From within, the cloud that was once a chaotic mix of powerful updrafts and downdrafts, of water droplets and ice crystals colliding at high speeds, of massive electrical charges being separated and discharged, gradually becomes quieter. The particles settle, the air currents calm, the cloud spreads out and thins, eventually dissipating into wisps that fade back into the general moisture of the atmosphere. But during its mature stage, during that period when updrafts and downdrafts coexisted, when ice and water mixed in specific ways, when everything aligned just right, during that time, the cloud became an enormous electrical generator. Nature, it seems, discovered how to build capacitors and batteries from nothing more than water and ice and moving air. The engineering is remarkable, really, when you stop to consider it. Of course, the cloud isn't consciously doing any of this. It's not trying to create lightning any more than a river is trying to carve a canyon, or a crystal is trying to grow into a particular shape. These things happen because physics dictates that they must, given the conditions. The universe is full of patterns that emerge from simple rules, and lightning is one of the most spectacular examples. You might imagine yourself as a researcher studying these clouds, perhaps flying through them in a specially equipped aircraft. Such flights are real. Scientists do this work, though it's dangerous and requires careful planning. They fly through thunderstorms with instruments that measure wind speed, temperature, humidity, and electric field strength. They collect particles to study their size and shape. They sometimes trigger lightning artificially to study its properties. What they've learned from these flights, combined with laboratory experiments and computer simulations, has given us a detailed understanding of how thunderstorms create lightning. It's a story that begins with something as simple as ice crystals colliding with small particles of graupel, soft hail, in the mixed phase region of the cloud. The collisions seem almost gentle, nothing particularly dramatic about them, and yet, these billions of tiny collisions, accumulated over time and space within the cloud, build towards something magnificent. The storm cloud at its peak is a marvel of natural engineering, typically about 10 to 15 kilometers tall, 5 to 10 kilometers wide, containing millions of tons of water in various forms, generating winds that can exceed 100 kilometers per hour, and producing electrical potential differences of hundreds of millions of volts, all from the simple process of warm air rising, water condensing, and ice forming. Let your mind rest with that image for a moment. A massive structure made of water and air, powered by the sun, following the laws of thermodynamics and electrostatics, creating one of the most recognizable phenomena in nature. There's something deeply satisfying about understanding how it works, about knowing that the lightning flash isn't magic or mystery, but the result of processes we can describe and predict. The cloud continues its life cycle, indifferent to our understanding of it. It will produce lightning for a time, then fade away, its water returning to the atmosphere or falling as rain. The conditions that created it will appear again on another day, in another place, and another storm will form. This pattern has repeated countless times over Earth's history, long before there were humans to witness it, and will continue long into the future. Chapter 4. Ice Crystals and Collision. Now we arrive at the heart of the matter. Lightning begins not with anything obviously electrical, but with ice. specifically with collisions between ice crystals and small particles of soft hail called graupel. These collisions, occurring millions of times throughout the cloud, are where electric charge begins to separate. To understand how ice can become electrically charged, we need to think about the structure of ice at the molecular level. Ice, as we mentioned earlier, forms a crystalline structure. Water molecules arrange themselves in a regular, repeating pattern. Each oxygen atom bonded to hydrogen atoms, each hydrogen atom forming weak bonds called hydrogen bonds with oxygen atoms in neighboring molecules. This structure isn't random. The angles between bonds are precise, dictated by the quantum mechanics of how electrons behave in the water molecule. The result is ice's characteristic hexagonal symmetry. That's why snowflakes, which are collections of ice crystals, tend to have six-fold symmetry in their shapes. It's not chance, it's geometry written into the fundamental nature of H2O. But ice crystals in clouds aren't perfect. They contain defects, places where the regular structure is interrupted. There might be an extra molecule squeezed in where it doesn't quite fit, or a missing molecule leaving a vacancy in the lattice. There might be an impurity, a molecule of something other than water incorporated into the structure. These defects are normal and inevitable. What's interesting about these defects is that they can affect the electrical properties of ice. In pure ice, water molecules are electrically neutral overall. But remember that each molecule is polar. The oxygen end is slightly negative. The hydrogen end is slightly positive. In the crystal structure, hydrogen bonds form when a hydrogen atom from one molecule sits close to an oxygen atom from another molecule. Sometimes, a proton, which is just a hydrogen nucleus, a single positive charge, can jump from one molecule to a neighboring molecule along a hydrogen bond. When this happens, it creates what scientists call an ionic defect in the ice crystal. One molecule ends up with an extra hydrogen ion, making it positively charged, while another molecule loses a hydrogen ion, leaving it negatively charged. These ionic defects can move through the ice crystal, carrying charge from one place to another. They're like mobile packets of electrical charge embedded in the crystal structure. In isolation, this wouldn't matter much. The defects would be randomly distributed, and the ice crystal would remain electrically neutral overall. But during collisions between ice crystals and graupel, something interesting happens. Graupel forms when supercooled water droplets collide with ice crystals and freeze on contact. The result is a small pellet of soft, opaque ice, usually a few millimeters in diameter. It's denser than a typical ice crystal but softer and lighter than true hail. In the mixed phase region of a thunderstorm cloud, where temperatures are between about 0 and -20 degrees Celsius, graupel and ice crystals coexist, both being carried around by the strong updrafts. When an ice crystal collides with a graupel particle, the collision itself is quite gentle. We're talking about relatively small particles moving through air, not solid objects crashing together. But during the brief moment of contact, something happens at the molecular level. Scientists believe that during the collision, those ionic defects we mentioned, the mobile charges in the ice structure, can transfer from one particle to the other. The exact mechanism is still debated, but the leading theory involves something called the thermoelectric effect. During the collision, there's a temperature difference between the graupel particle and the ice crystal. Graupel, being denser and larger, tends to be slightly warmer than the small ice crystals around it. This temperature difference, even though it's small, affects how ionic defects behave during the collision. Laboratory experiments have shown that when ice crystals at temperatures colder than about -10 or -15 degrees Celsius collide with warmer graupel, the ice crystals tend to pick up positive charges while the graupel becomes negatively charged. It's a subtle effect, each collision transferring only a tiny amount of charge, but remember that we're talking about billions and billions of collisions occurring throughout the cloud over the course of many minutes. Picture it happening. An ice crystal, perhaps a small dendrite with delicate arms, tumbles through the cloud. It encounters a graupel particle, collides gently, bounces off. In that instant of contact, a few ionic defects transfer, and the ice crystal acquires a slight positive charge. The graupel, now slightly negative, continues on its way. Both particles keep moving through the cloud, and both will likely collide with other particles many more times. This process, called the non-inductive charging mechanism, non-inductive because it doesn't require any external electric field to work, is thought to be the primary way thunderstorm clouds generate and separate electric charge. It's remarkably simple in concept, really. Ice crystals and graupel collide, charges transfer, and because the particles have different properties, they end up in different parts of the cloud. Here's where the size and weight of the particles becomes crucial. Ice crystals are light and small, easily carried upward by even moderate updrafts. Graupel particles are heavier and larger, and while updrafts can support them for a time, they tend to fall or remain in the lower parts of the strong updraft region. This physical separation of light ice crystals and heavy graupel leads directly to electrical charge separation. The positively charged ice crystals are carried to the upper parts of the cloud. There, they accumulate, creating a region of net positive charge. Meanwhile, the negatively charged graupel particles remain in the middle and lower parts of the cloud, creating a region of net negative charge. Some graupel does fall out of the cloud as precipitation, and when it does, it carries negative charge toward the ground, but much of it remains suspended or circulating in the cloud's middle regions. Over time, and we're talking about perhaps 15 or 20 minutes in a developing storm, this separation of charge becomes substantial. The upper part of the cloud accumulates a positive charge measured in tens of coulombs. The middle part of the cloud accumulates a negative charge of similar magnitude. For perspective, 1 coulomb is the amount of charge that flows past a point in an electrical circuit in 1 second when the current is 1 ampere. Lightning will eventually transfer charges measured in tens or hundreds of coulombs in less than a second. There's also often a smaller region of positive charge at the very bottom of the cloud, formed by various mechanisms, including the descent of positively charged particles and what's called the screening layer effect. This creates what meteorologists call the tripolar structure of a thunderstorm. Positive charge at the top, negative in the middle, and a smaller positive region at the bottom. This structure is not perfectly organized, of course. Real clouds are messy, with pockets and streamers of charge distributed in complex patterns. But the overall structure, positive above, negative in the middle, is consistent across different thunderstorms and different locations around the world. It's a pattern that emerges reliably from the physics of ice collision and particle separation. You might be starting to feel the weight of sleep pressing more heavily on your eyes. That's perfectly fine. Let yourself drift if you need to. The science will be here when you return, or perhaps your sleeping mind will process these ideas in its own way, making connections that your waking mind might miss. The collisions continue. Ice crystals tumble and spin in the turbulent air. Graupel particles bounce and jostle, and with each contact, minute quantities of charge change hands. It's a process that happens on the smallest scales. Individual particles just micrometers or millimeters in size, but accumulates to create effects on the grandest scales. Electrical potential differences, large enough to tear apart the very air itself. Because that's what lightning is. In the end, it's air breaking down, its molecules being ripped apart by electrical forces so strong that they overcome the insulating properties of the atmosphere itself. But before we get to that dramatic moment, before we watch the lightning channel form and pulse with energy, we need to understand what happens as the charge continues to build. We need to see how the cloud becomes not just electrically charged, but charged to the breaking point. Chapter 5. The Separation of Charges. As the collisions between ice and graupel continue, as the updrafts keep carrying particles through different regions of the cloud, as minutes pass and the storm matures, something remarkable happens. The relatively modest charge imbalances created by billions of individual collisions add up to create an enormous separation of charge within the cloud. Think of it like this. Imagine you have two enormous containers, separated by some distance. You're moving grains of sand from one container to the other, one grain at a time. Each grain is insignificant, nearly weightless. But if you move enough grains, if you keep at it long enough, eventually you'll have transferred a significant mass of sand from one container to the other. The charge separation in a thunderstorm cloud works similarly, except instead of sand grains, we're moving ionic defects, and instead of mass, we're accumulating electrical charge. The amount of charge that accumulates is surprisingly large. Scientists estimate that a typical mature thunderstorm cloud contains perhaps 20 to 40 coulombs of positive charge in its upper regions, and a similar magnitude of negative charge in its middle regions. To put that in perspective, a standard AA battery might deliver a current of about 1 ampere for a few hours, which means it moves a few thousand coulombs over its lifetime. The thunderstorm accumulates similar amounts of charge in just minutes, and it's prepared to discharge much of it in fractions of a second. This separation of charge creates what physicists call an electric field within and around the cloud. An electric field is a bit abstract to visualize, but you can think of it as a kind of tension in space, a tendency for charged particles to be pushed in certain directions. Positive charges experience a force pushing them one way. Negative charges experience a force pushing them the opposite way. The strength of an electric field is measured in volts per meter. In ordinary air at Earth's surface, there's actually a small electric field present all the time, typically around 100 volts per meter pointing downward. This is related to the fact that Earth's surface carries a slight negative charge, while the upper atmosphere is slightly positive. A topic for another time. But 100 volts per meter is very weak, and we never notice it in our daily lives. Inside a developing thunderstorm, the electric field strength is orders of magnitude larger. As charge separation increases, the field strength grows. In the regions between the positive upper charge and the negative middle charge, the field can reach 100,000 or even 200,000 volts per meter. That's more than 1,000 times stronger than the background field. You might wonder why this strong electric field doesn't immediately cause lightning? The answer has to do with the electrical properties of air. Air is normally a good insulator. It doesn't conduct electricity easily. For air to conduct electricity, something has to break down its insulating properties. The molecules that make up air, mostly nitrogen and oxygen, have to be ionized, torn apart into positive and negative fragments that can carry electrical current. This breakdown of air requires an electric field strength of roughly 3 million volts per meter. That's the threshold at which air can no longer resist the electrical force and begins to conduct. It's called the dielectric breakdown strength of air. At fields weaker than this, air remains an insulator, and charges can accumulate without discharging. So the thunderstorm cloud builds its charge separation, creating ever stronger electric fields within itself and between itself and the ground below. The field reaches 100,000 volts per meter, then 150,000, then 200,000. It's approaching the breakdown threshold, but it hasn't reached it yet. The storm is like a battery being charged, its voltage climbing higher and higher. As the electric field strengthens, subtle effects begin to occur. The field itself starts to influence how particles move and collide within the cloud. Charged particles experience forces from the electric field in addition to the drag from air currents. The field also affects the behavior of any ions or free electrons that happen to be present in the cloud. Cosmic rays constantly create a small number of ions in the atmosphere, and these respond to electric fields. Near sharp points or irregularities, perhaps at the tip of an ice crystal, perhaps at some small-scale inhomogeneity in the cloud structure, the electric field can be locally enhanced. This is the same principle behind lightning rods. Electric fields are stronger near pointed objects. In these regions of enhanced field strength, the field might reach or exceed the breakdown threshold, even while the average field in the cloud is still below it. When the field exceeds 3 million volts per meter in some small region, a remarkable thing happens. A few electrons get accelerated to high enough energies that when they collide with air molecules, they knock other electrons loose. Each of these new electrons can then be accelerated by the field and knock loose more electrons when they collide with other molecules. It's a cascade effect called an electron avalanche. These avalanches create small channels of ionized air, perhaps just a few centimeters or meters long. The ionized air conducts electricity, allowing charge to flow through these tiny channels. But the amount of charge that flows through these small avalanches isn't enough to significantly discharge the cloud. They're more like tiny sparks, precursors to the main event. What's needed for lightning to occur is a much longer conducting channel, one that extends either from the main negative charge region to the positive region within the cloud, or from the cloud to the ground. Creating such a channel requires a special process, one that doesn't happen all at once but develops in stages. We'll explore that process in the next chapter. But for now, let's appreciate the state the cloud has reached. The mature thunderstorm, with its separated charges creating strong electric fields, is primed for lightning. It's reached an unstable state, one that can't persist indefinitely. The electrical stress within the cloud, the tension represented by that strong electric field, needs release. The cloud has done the work of separating charge, fighting against the natural tendency for opposite charges to come together. It's like stretching a rubber band. You're storing energy, creating a situation that wants to snap back to equilibrium. In the case of the cloud, Equilibrium means negative and positive charges coming back together, neutralizing each other. The air's insulating properties have prevented this from happening so far, but those properties are about to be overcome. The stage is set for one of the most spectacular energy releases in nature, but it's worth pausing here to appreciate what's been accomplished. Starting from simple processes: water evaporation, air rising, droplets forming, ice crystals growing, particles colliding. The cloud has created a powerful electrical generator. No moving parts in the traditional sense, no copper wires or magnetic fields, just water in its various forms being moved through different temperature zones by natural convection. And the result is electrical potential differences large enough to be measured in hundreds of millions of volts. Let your breathing deepen further. Feel the weight of your body against whatever surface you're resting on. The thunderstorm continues its work, indifferent to our understanding, following the laws of physics with the same reliability that governs everything in the universe. There's something almost meditative about contemplating these natural processes, seeing how complexity emerges from simple rules applied over and over again. The next time you see a thunderstorm, perhaps you'll think about what's happening inside it. The ice crystals tumbling in updrafts, the grapple particles accumulating negative charge, the growing separation of charges creating stronger and stronger electric fields. All of it building toward that moment when the air itself will break down and lightning will flash. Chapter 6: Building the Electric Field. The electric field within and around the thunderstorm continues to strengthen. With each passing minute, more charge is separated. More positive ions accumulate in the upper regions of the cloud. More negative charge collects in the middle regions. The field between these charge centers grows more intense, and crucially, the field extends beyond the cloud itself, reaching down toward the ground below. To understand what happens next, it helps to think about electric fields in more detail. An electric field represents the force that a charged particle would experience at any point in space. The field has both magnitude, how strong the force would be, and direction, which way the force would push. In the region between the negative charge in the cloud and the positive charge induced on the ground below, the field points downward. Wait, positive charge on the ground? We haven't mentioned that yet. Here's what happens. As the negative charge accumulates in the lower portions of the cloud, it repels negative charges in the ground directly beneath it. Remember, like charges repel, the negative charges in the ground, which are mobile electrons in soil, water, and any conducting materials, are pushed away, leaving behind positive charges. This induced positive charge on the ground is exactly equal in magnitude to the negative charge in the cloud above. Though spread over a larger area, it follows the cloud as the storm moves. Like a shadow made of positive charge, the ground doesn't actively create this charge. It's simply a rearrangement of charges that were already there, pushed around by the electric field from the cloud. Between the negative charge in the cloud and the positive charge on the ground, a strong electric field now exists. The field strength varies with location, being strongest directly beneath the most intensely charged part of the cloud and weaker further away. Near the surface, in ordinary conditions, this field might reach 10,000 to 20,000 volts per meter, much stronger than the normal atmospheric field, but still far below the breakdown threshold of 3 million volts per meter. However, here's a crucial point. The field is not uniform. It's much stronger in some places than others, particularly near tall objects on the ground, trees, buildings, towers, or even a person standing in an open field. The field becomes concentrated. This is the lightning rod effect we mentioned earlier. The electric field near a pointed or elevated object can be 10 times stronger than the average field nearby. If a tall object is tall enough, and the cloud's charge is strong enough, the field near the top of that object might reach or exceed the breakdown threshold, even while the field at ground level is still moderate. When this happens, a small corona discharge can begin. A faint, continuous discharge of electricity from the tip of the object into the surrounding air. This ionizes the air near the tip, creating a small region of conducting plasma. Similarly, within the cloud, regions of locally enhanced electric field exist. These might be near the edge of the main charge region, or near small-scale structures within the cloud where charge has concentrated. In these regions, the field can exceed the breakdown threshold before it does elsewhere. These regions of strong field are where lightning initiation is thought to begin. The exact details of how lightning starts are still not completely understood. It's difficult to observe the very beginning of a lightning flash, since it happens inside the cloud where we can't see it directly, and it develops very quickly. But scientists have some good evidence for what probably occurs. It likely begins with one or more of those electron avalanches we mentioned earlier. In a region where the field is strong enough, an initial electron gets accelerated, collides with a molecule, knocks loose another electron, and a cascade develops. This creates a small channel of ionized air, perhaps a few meters long. Normally, this avalanche would fade away as the electrons diffuse and recombine with positive ions. But if conditions are right, if the electric field is strong enough and oriented correctly, something else can happen. The ionized channel from one avalanche can modify the local electric field in a way that triggers more avalanches nearby. These avalanches can connect, forming a longer conducting channel. This is the beginning of what's called a leader, a channel of ionized air that propagates through the cloud, extending the conducting path from the initial charge region toward another region of opposite charge. The leader doesn't move smoothly. Instead, it advances in steps, each step extending the channel by perhaps 50 to 100 meters, then pausing for perhaps 50 microseconds before the next step. Why does it move in steps? The current thinking is that each step represents a successful series of electron avalanches that extend the ionized channel. Between steps, there's a brief period where charge flows into the tip of the leader, building up the field at the tip until it's strong enough to trigger the next series of avalanches. It's a bit like a reaching motion. Extend, pause, extend, pause, gradually lengthening the conducting path. Inside the cloud, a leader might propagate between the negative charge region and the positive charge region, creating a conducting channel between them. When the leader successfully bridges the gap, charge can flow through this channel, neutralizing some of the separated charge. This creates what's called an intracloud or cloud-to-cloud lightning flash, the type of lightning that illuminates clouds from within but doesn't reach the ground. But sometimes, perhaps 30% of the time, depending on conditions, a leader extends downward from the cloud toward the ground. This is the beginning of a cloud-to-ground lightning strike, the type that's most dramatic and most dangerous. This downward moving leader is called a stepped leader, and it's the first stage of the most recognized form of lightning. The stepped leader moves downward in discrete steps, each extending the conducting channel closer to the ground. It branches as it goes, creating multiple paths simultaneously, though usually only one path will ultimately complete the connection to the ground. The leader carries negative charge downward, extending the negative charge region of the cloud toward the Earth's surface. As the stepped leader approaches the ground, the electric field at the Earth's surface intensifies dramatically. Remember those induced positive charges on the ground? As the negative leader gets closer, the attraction between opposite charges becomes very strong. The field near any elevated object becomes extreme, possibly reaching or exceeding the breakdown threshold. When the stepped leader gets within perhaps 50 or 100 meters of the ground, and this is a rough figure, varying with conditions, something remarkable happens. From tall objects on the ground, upward leaders begin to form. These are similar to the stepped leader but moving upward instead of down. They're reaching up to meet the descending leader, like hands reaching toward each other. Multiple upward leaders might form from different objects, perhaps from a tree, a building, a tower. They race upward, competing to be the first to connect with the stepped leader. The winner of this race is the object that will be struck by lightning. The moment one of the upward leaders makes contact with the stepped leader, a complete conducting channel exists between cloud and ground. This is the moment of connection, and it marks the end of the stepped leader phase. But it's not yet the bright flash we recognize as lightning. That comes in the next phase, the return stroke, which we'll explore in detail in the coming chapter. For now, picture the scene. A conducting channel now extends from the negative charge region in the cloud down through kilometers of air, branching and rebranching, finally connecting to an object on the ground. The channel is perhaps 1 to 5 centimeters in diameter, composed of ionized air heated to thousands of degrees. It's essentially a pipe of plasma connecting cloud and earth. Along this channel, enormous amounts of charge are about to flow. The channel itself is like a wire that's been dropped between the terminals of a giant battery. And just as connecting a wire to a battery causes current to flow, connecting the cloud to ground through this ionized channel will cause a massive electrical discharge. The stage is set. The charges have been separated by the patient work of billions of ice collisions. The electric field has built to extraordinary strength. A conducting channel has been painstakingly constructed, step by step, through the insulating atmosphere. Everything is now in place for the main event, the brilliant, nearly instantaneous discharge of energy we call lightning. Take a slow breath. Let your muscles relax further. The science has brought us to the brink of understanding lightning itself. In the next chapter, we'll watch as that energy releases, as the return stroke races back up the channel, as the plasma heats to temperatures exceeding the surface of the sun, as light bursts forth in that characteristic brilliant flash. But for now, rest in this moment of potential, this charged anticipation before the discharge. Chapter 7. The Stepped Leader's Descent. Let's slow down and examine the stepped leader in more detail, for it's one of the most fascinating and least understood aspects of lightning. This invisible process, hidden from our eyes, happening in the fraction of a second before the visible flash, is where much of the intricate physics of lightning occurs. The stepped leader typically begins in the negative charge region of the cloud. usually at an altitude of perhaps 5 to 8 kilometers above the ground. In this region, the electric field has reached a strength sufficient to initiate leader formation. Remember those electron avalanches we discussed? Many of them have been occurring in this region, creating small, transient channels of ionized air. At some point, conditions align perfectly. Perhaps several avalanches connect in just the right way. Perhaps the local field strength peaks at just the right moment. Whatever the exact trigger, a leader begins to propagate. Unlike the brief, flickering avalanches that came before, this leader is more stable, more organized. It extends a conducting channel downward, away from the main negative charge region. The stepped leader doesn't move continuously. Instead, it advances in discrete steps, each step happening very quickly, in perhaps 1 microsecond, but with pauses of 50 microseconds or so between steps. During the step itself, the leader extends by perhaps 50 meters, creating new ionized channel where there was previously just insulating air. Then it pauses, and charge flows into the newly created channel section, preparing for the next step. You might imagine what this would look like if you could see it, which normally you can't. It's too faint and too fast. But high-speed cameras can capture it, and what they show is remarkable. The leader appears as a faint, glowing channel that jumps downward in distinct increments, like a crack propagating through glass, but happening in mid-air. With each step, the channel extends further toward the ground, often branching, creating multiple paths. The physics of how the stepped leader propagates is complex. At the tip of the leader, the electric field is extremely strong, much stronger than in the surrounding air. This enhanced field at the tip is what triggers the next electron avalanche, the next step. Electrons in the tip region are accelerated to high energies by this strong field. When they collide with air molecules, mostly nitrogen and oxygen, they can knock electrons loose from those molecules, creating positive ions and more free electrons. These new electrons are also accelerated by the field, and they knock loose still more electrons when they collide with other molecules. It's a chain reaction, an avalanche that rapidly creates a channel of ionized air extending from the leader tip. This new section of ionized channel is hot, thousands of degrees Celsius, because the collisions between accelerated electrons and molecules transfer energy, which appears as heat. Once this new section of channel is created, charge begins to flow into it from the leader behind it. The channel is conductive now, so negative charge from the cloud can flow down through the existing leader channel and into the newly formed section. This charge flow partially neutralizes the charge in the new section, and it also sets up conditions for the next step by concentrating charge at the new tip of the leader. Between steps, during those 50 microsecond pauses, the leader glows dimly as charge flows into it. The current during these pauses is perhaps 100 to a few hundred amperes. Significant, but not nearly as much as will flow during the return stroke. This current heats the channel, maintains its ionization, and prepares it for the next step forward. As the stepped leader descends, it typically travels at speeds of about 100 to 200 kilometers per second. That might sound fast, and it is, about 1,000th the speed of light, but it's actually quite slow for an electrical phenomenon. The reason it's slow is that the step-pause progression takes time. The leader has to repeatedly break down new air, extend its channel incrementally, pause to recharge, then break down more air. The stepped leader also branches extensively. Almost from its beginning, multiple paths diverge from the main channel, creating what looks like an upside-down tree or a river system. Some of these branches will extend for hundreds of meters before stalling. Others will continue downward, remaining active as the leader progresses. The branching happens because the electrical breakdown of air isn't uniform. There are variations in air density, moisture content, and the presence of ions from cosmic rays or other sources. Where conditions favor breakdown, a new branch can form. From the ground, none of this is visible to the naked eye. The stepped leader is too faint. What people do sometimes report is a feeling of unease. Just before a lightning strike, a sense that something is about to happen. This might be related to the strong electric field that develops as the leader approaches. The field can be strong enough to cause hair to stand on end or create a tingling sensation on skin. These are signs that you're in imminent danger of being struck, by the way, and you should immediately seek shelter. As the stepped leader gets closer to the ground, within perhaps 200 meters, its effects become more pronounced. The electric field at the Earth's surface intensifies dramatically. Any tall, pointed object experiences a particularly strong field at its tip. The air around such objects begins to ionize, glowing faintly in what's called a corona discharge. This discharge carries a small current from the object into the air, creating positive ions that drift upward. The stepped leader continues its descent, branching and rebranching, some branches dying out while others continue. It's a race, in a sense, between multiple branches to see which one will reach the ground first. But really, it's not just about reaching the ground. It's about connecting with one of the upward leaders that are starting to form from ground objects. These upward leaders, also called upward streamers or connecting leaders, begin when the field near a tall object exceeds the breakdown threshold. Suddenly, from the tip of a tree or building or tower, a channel of ionized air begins to propagate upward. These upward leaders move in a similar stepped fashion to the downward stepped leader, though usually with smaller steps and moving somewhat more slowly. Multiple upward leaders might form from different objects, all reaching upward toward the descending stepped leader. It's an extraordinary sight in high-speed video, like fingers reaching up from the earth toward a branching network descending from above. The first upward leader to make contact with a branch of the stepped leader wins. In a sense, that object will be the attachment point for the lightning strike. The moment of contact typically occurs when the stepped leader is between 10 and 100 meters above the ground, though this varies significantly depending on conditions and the height of objects on the ground. Taller objects, by reaching up with upward leaders, effectively extend their height, increasing the likelihood they'll be struck. When contact is made, the situation changes instantaneously. Before contact, there was a conducting channel extending from the cloud toward the ground, but not quite reaching it. The channel was at the electrical potential of the cloud's negative charge region, perhaps 100 million volts different from ground potential, but it was an isolated conductor, not connected to anything. The moment the upward leader connects with the stepped leader, this changes. Now there's a continuous conducting path from cloud to ground. The channel is connected to both the massive charge reservoir in the cloud and the Earth itself. which can supply or absorb any amount of charge at ground potential. This connection removes the constraint that kept charge from flowing freely. What happens next is almost unimaginably fast. Charge begins to pour down the conducting channel, flowing from cloud to earth. But even more dramatic than this downward flow of charge is what happens to the channel itself. The sudden flow of current heats the channel explosively. The temperature jumps to 30,000 Kelvin or more, several times hotter than the surface of the sun. The channel becomes a brilliant cylinder of plasma, expanding rapidly, glowing with intense white light. This heating and brightening doesn't happen uniformly throughout the channel. Instead, it begins at the point of attachment to the ground and propagates upward, back toward the cloud, traveling at about 1/3 the speed of light. This upward propagating wave of heating and brightening is called the return stroke, and it's what we actually see as lightning, the brilliant flash that illuminates the landscape. But we're getting ahead of ourselves. Before we explore the return stroke in full detail, let's pause to appreciate what the stepped leader has accomplished. Starting from nothing but strong electric fields in the cloud, it has created a conducting channel several kilometers long through air that normally insulates. It has done so incrementally, step by step, each step a small miracle of plasma physics, and it has found its way to the ground, connecting cloud and earth in a way that sets the stage for an enormous energy release. The sophistication of the physics involved in the stepped leader is remarkable. The process self-organizes, requiring no external control or guidance. It emerges from the interaction between electric fields, electron avalanches, and the properties of air. Yet the result is repeatable and consistent. Stepped leaders always behave in recognizably similar ways, even though no two are exactly alike. Let your mind drift for a moment, considering this invisible process. Before every lightning flash you've ever seen, a stepped leader descended from the clouds, following the laws of physics, creating the path that would channel the subsequent discharge. The flash you saw was the return stroke, but the return stroke could not occur without the stepped leader preparing the way. Chapter 8. The Return Stroke, Lightning's Brilliance. The moment the connection is made between the downward stepped leader and the upward connecting leader, everything changes. In less than a millionth of a second, a conducting channel several kilometers long suddenly connects a massive reservoir of negative charge in the cloud to the positively charged ground. The result is one of the most dramatic energy releases in nature. The return stroke begins at the point of attachment to the ground and propagates upward through the channel created by the stepped leader. Think of it like this. Before the connection was made, the stepped leader channel was filled with relatively small amounts of charge, distributed along its length. The channel was ionized and conductive, but it wasn't yet carrying the massive current it's capable of carrying. When connection occurs, the bottom of the channel suddenly becomes connected to ground, to Earth, which is an essentially infinite reservoir of charge at zero electrical potential. The negative charge that had been in the bottom section of the leader can now neutralize by flowing to ground. As it does, this section of the channel becomes electrically neutral or close to it. But remember, the channel extends several kilometers upward, with more charge along its length, and ultimately connecting to the massive charge reservoir in the cloud. Once the bottom section neutralizes, the section just above it is now connected to ground through a conductive path. its charge can flow to ground as well, and so on, section by section, moving upward through the channel. This upward progression of neutralization is the return stroke. It moves at about 1/3 the speed of light, roughly 100,000 kilometers per second. That means it takes only about 30 microseconds for the return stroke to travel the full length of a typical lightning channel from ground to cloud. It's this extraordinary speed that makes lightning appear to our eyes as an instantaneous flash rather than a progression. The current in the return stroke is enormous, typically 30,000 amperes, sometimes much more. This is hundreds of times greater than the current in the stepped leader. When this much current flows through the relatively narrow channel, remember, it's only a few centimeters in diameter. The heating is explosive. The air in the channel, already ionized and hot from the stepped leader phase, suddenly heats to temperatures of 30,000 Kelvin or more. To put that in perspective, the surface of the sun is about 6,000 Kelvin. The lightning channel becomes several times hotter than the sun's surface, though only for a fraction of a second. At these temperatures, the air becomes a plasma, a state of matter where electrons are stripped from atoms, creating a mixture of ions and free electrons. This plasma is an excellent conductor of electricity, which is why so much current can flow through it. The plasma is also extremely bright. Hot objects emit light, and the hotter they are, the more light they emit, and the more energetic that light is. A lightning channel, at 30,000 Kelvin, emits intense white light, dominated by ultraviolet wavelengths. It's this light that we see as lightning, the brilliant flash that illuminates the landscape, casting stark shadows, making the clouds glow from within. That's the light from the return stroke, from a channel of plasma hotter than the sun. The light is so bright that it can temporarily dazzle your eyes if you're looking directly at it. It's bright enough to photograph by, to read by, if you happen to be holding a book during a storm, though you really shouldn't be outside with a book during a lightning storm. The extreme heating of the channel also causes it to expand violently. The air around the channel is suddenly compressed as the hot plasma tries to expand. This expansion happens faster than the speed of sound, creating a shock wave that propagates outward from the channel. This shock wave is what we hear as thunder, though we'll explore that in more detail in the next chapter. The return stroke lasts only about 100 microseconds, 1/10,000th of a second. During this brief time, it transfers a significant fraction of the charge that was stored in the negative charge region of the cloud down to the ground. Typically, a return stroke might transfer 5 or 10 coulombs of charge, though some transfer much more. As the return stroke progresses up the channel, it illuminates the various branches that were created by the stepped leader. Not all branches carry the same current, and some may not carry any significant return stroke current at all. The branches that do carry current light up brilliantly, creating that characteristic forked appearance of cloud-to-ground lightning. If you've ever seen lightning photographs that show multiple parallel zigzag channels, those aren't separate lightning strikes. They're separate branches of the same strike, all illuminated during the return stroke. The whole tree-like structure lights up nearly simultaneously. Remember, the return stroke moves at 1/3 the speed of light. So even a structure kilometers across is illuminated in just a tiny fraction of a second. After the initial return stroke finishes, you might think the lightning is over. Sometimes it is a single stroke flash. but more often, the process continues. There's still significant charge in the cloud's negative charge region. The conducting channel created by the stepped leader and lit up by the return stroke hasn't disappeared. It's still there, still hot, still ionized, still conductive. Within a few thousandths of a second after the first return stroke, another leader can form using the same conducting channel. This is called a dart leader, and it's different from the stepped leader. The dart leader doesn't move in steps. Instead, it propagates continuously down the existing channel, moving much faster than the stepped leader did, typically about 10,000 kilometers per second, or about 1/30th the speed of light. The dart leader is like someone tracing over an existing pencil line with a pen. The path is already there, already established. So creating the dart leader is easier and faster than creating the original stepped leader was. The dart leader carries negative charge from the cloud down through the channel, preparing it for another return stroke. When the dart leader reaches the ground, another return stroke occurs, just like the first one. This subsequent return stroke again heats the channel to extreme temperatures, again produces a brilliant flash of light, again transfers several coulombs of charge from cloud to ground. To an observer, this appears as a second flash, though it's using the same channel as the first flash. This process can repeat multiple times. A typical lightning flash consists of 3 or 4 strokes, but some contain 10 or more. Each stroke follows the same pattern. Dart leader descends, return stroke ascends, channel heats and brightens, charge is transferred. The time interval between strokes is typically about 40 to 80 milliseconds. This is why lightning sometimes appears to flicker. Each individual return stroke is too brief for your eye to resolve. It's over in 100 microseconds. But if there are 4 strokes, separated by 50 milliseconds each, the total duration of the lightning flash is about 200 milliseconds, which is long enough for your eye to perceive as a sequence rather than a single event. The flickering you see is the sequence of return strokes. From a distance, especially at night, this flickering gives lightning its characteristic appearance. It's not a single flash that turns on and off, but a series of distinct pulses, each one following nearly the same path through the air, each one releasing energy that was built up during the time between strokes. The total charge transferred by a multi-stroke flash can be substantial. If each return stroke transfers 5 coulombs, and there are 4 strokes, that's 20 coulombs total. The total energy dissipated can be about 1 billion joules, which is equivalent to about 250 kilowatt hours of electricity, enough to power an average home for more than a week, though it's released in less than a second and in a form that's extremely difficult to capture and use. Let yourself imagine standing at a safe distance from a lightning strike, watching the brilliant channel light up again and again, flickering 3 or 4 times in rapid succession. Each flash momentarily turns night into day, casting stark shadows, making every detail of the landscape visible. Then darkness returns, leaving an afterimage on your retina and a sense of awe at the power of nature. The return stroke is the part of lightning that we're most familiar with, the part that's most visible and most dramatic. But as we've seen, it's just one phase of a complex process that begins with ice collisions in clouds, continues with charge separation and electric field buildup, proceeds through the invisible descent of a stepped leader, and culminates in this brilliant, nearly instantaneous discharge. Understanding the return stroke helps us appreciate several things about lightning. First, the incredible amounts of energy involved. Second, the extreme conditions, temperatures hotter than the sun's surface, currents measured in tens of thousands of amperes that exist in that narrow channel for tiny fractions of a second. Third, the multi-stroke nature of many lightning flashes, explaining why they flicker rather than appearing as single, brief pulses. Each of these aspects emerges from fundamental physics. The charge separation creates electrical potential energy. The stepped leader creates the conducting path. The return stroke releases that energy as heat and light, governed by the relationship between current, resistance, and power dissipation. Thunder, which we'll explore next, follows inevitably from the extreme heating of air. It's all connected, each piece following necessarily from what came before, the whole process emerging from the simple fact that ice and graupel collide in the mixed-phase region of thunderstorm clouds. From such simple beginnings, nature creates lightning. Chapter 9. Thunder's rolling voice. Thunder is lightning's companion, inseparable from the flash, though delayed in reaching our ears. Understanding: thunder requires understanding sound, which is simply waves of compression and rarefaction, alternating regions of slightly higher and slightly lower air pressure, propagating through the atmosphere. When the return stroke heats the lightning channel to 30,000 Kelvin, the air in and around that channel expands explosively. This expansion happens in less than a microsecond, faster than sound can travel, which means the expanding channel creates a shock wave, a moving wall of compressed air that propagates outward from the lightning channel in all directions. Initially, this shock wave is very strong, with pressures perhaps 10 times atmospheric pressure right at the channel boundary. But shock waves weaken as they propagate. Within about 10 meters of the channel, the shock has weakened enough that it's no longer a shock wave, but an ordinary sound wave, a pressure disturbance that propagates at the speed of sound, about 340 meters per second at sea level. This sound wave is what we hear as thunder. But thunder has distinctive characteristics that tell us something about the lightning that created it. Unlike the simple crack or pop you might hear from a small spark, thunder can rumble for many seconds, varying in loudness and pitch as it progresses. These characteristics come from the geometry of the lightning channel and the way sound propagates through the atmosphere. Consider a lightning channel extending from cloud to ground, perhaps 5 kilometers long. When the return stroke occurs, the entire length of this channel heats and expands nearly simultaneously, within about 30 microseconds, as we discussed. This means that sound is being generated from every point along a 5-kilometer-long source, all at essentially the same time. But this sound doesn't reach an observer on the ground at the same time. Sound from the nearest part of the channel, perhaps the point where it touched down, if you're close to the strike point, reaches you first. Sound from points further along the channel has to travel further to reach you, so it arrives later. Sound from the top of the channel, 5 kilometers away and several kilometers high, arrives substantially later. Given that sound travels at about 340 meters per second, sound from a point 1 kilometer away takes about 3 seconds to reach you. Sound from a point 5 kilometers away takes about 15 seconds. So if you're near a lightning strike, you'll hear thunder that lasts for 15 seconds or more, with sound from different parts of the channel reaching you at different times. This explains why thunder rumbles rather than happening all at once. The rumble is the extended duration caused by sound arriving from different distances. If lightning were a point source, a spark in a single location, thunder would be a single sharp report. But because lightning is an extended source, a long channel stretched through space, thunder is drawn out in time. The pitch and intensity of thunder vary for other reasons too. Sound from the closest parts of the channel tends to be sharper and higher pitched, sometimes a distinct crack or bang. This is because the shock wave from those parts hasn't traveled as far, hasn't weakened as much, and still contains higher frequency components. Sound from distant parts of the channel is more of a low rumble because high frequencies are absorbed more readily by the atmosphere than low frequencies. The further sound travels, the more the high frequencies are filtered out, leaving only the low rumbles. The shape of the lightning channel also matters. Most lightning channels are not straight but are bent and branched, zigzagging as they propagated through regions of varying air properties during the stepped leader phase. This means that different parts of the channel are at different distances from any given observer, creating a complex pattern of arrival times for sound. Furthermore, sound from the channel doesn't travel in straight lines from source to observer. Sound waves can be refracted, bent, by temperature and wind gradients in the atmosphere. They can be reflected from the ground or from the bases of clouds. They can be absorbed or scattered by rain, fog, or trees. All of these factors modify the sound that reaches an observer, changing its character. Temperature gradients are particularly important. On a typical day, temperature decreases with altitude in the lower atmosphere. Sound travels faster in warm air than in cold air, so sound waves propagating through the atmosphere tend to bend upward, away from the surface. This is why thunder from a distant lightning strike sometimes can't be heard at all. The sound waves have refracted upward and passed over the observer without reaching ground level. On some nights, particularly after a hot day, the situation reverses. A layer of cool air might settle near the ground with warmer air above it. In this case, sound waves bend downward toward the surface and can propagate for much greater distances than usual. On such nights, thunder can sometimes be heard from lightning strikes dozens of kilometers away. The classic rule of thumb for estimating distance to a lightning strike is to count the seconds between seeing the flash and hearing the thunder, then divide by 5 if you're thinking in miles, or 3 if you're thinking in kilometers. This works because light from the flash reaches you essentially instantaneously. Light travels so fast that the delay is imperceptible, while sound takes about 5 seconds to travel a mile or 3 seconds to travel a kilometer. So if you see lightning and hear thunder 5 seconds later, the lightning was about 1 mile or 1.6 kilometers away. If the delay is 15 seconds, the lightning was about 3 miles or 5 kilometers away. Beyond about 20 or 30 kilometers, thunder typically can't be heard at all. Not because there isn't thunder, but because the sound has weakened too much or refracted too far upward to reach your ears. There's a specific kind of thunder that deserves mention: the sharp crack that sometimes accompanies a very close lightning strike. If lightning strikes within 100 meters or so, the thunder can be startlingly loud and immediate, arriving almost simultaneously with the flash. This thunder has a distinctly different character from the rolling rumbles of more distant strikes. It's sharp, sudden, sometimes almost painful in its intensity. This is because you're close enough that you're hearing the initial shock wave before it has fully transitioned into an ordinary sound wave. Thunder can also echo off buildings, hills, or other large objects, creating additional rumbles that arrive after the direct sound. In mountainous terrain or urban environments with tall buildings, these echoes can be significant, prolonging the thunder and giving it a more complex character. The result can be a thunder that seems to roll around the sky, bouncing from place to place, lasting for half a minute or more. One question people sometimes ask is whether you can have lightning without thunder or thunder without lightning. The answer is no, at least not in the normal sense. Every lightning flash produces thunder. The extreme heating of air ensures this. But you can see lightning without hearing thunder if the strike is too far away, or if atmospheric conditions carry the sound away from you. And you can sometimes hear thunder without seeing lightning if clouds or terrain block your view of the flash, or if the lightning is entirely within clouds. Speaking of intracloud lightning, that type that stays entirely within the cloud rather than reaching ground, it also produces thunder, though the character might be somewhat different. Intracloud lightning channels are often shorter than cloud-to-ground channels and may be at higher altitudes, so the thunder might be more muffled or distant sounding, but the physics is the same. Rapid heating causes expansion, causes a shock wave, causes sound. Thunder serves a practical purpose for people caught in storms, because you hear thunder from lightning that was close enough for the sound to reach you. Hearing thunder means you're within range of lightning strikes. The saying, "When thunder roars, go indoors," is based on this principle. If you can hear thunder, the storm is close enough to potentially strike your location, and you should seek shelter. Some people find thunder frightening, and that's understandable. It can be loud, sudden, and unexpected. But understanding what thunder is, just sound, just waves of compressed and rarefied air caused by rapid heating, can make it less frightening. It's the result of an extraordinary physical process, yes, but it's not fundamentally different from any other sound. The lightning itself is what's dangerous, not the thunder. Others find thunder soothing, particularly the deep, distant rumbles of a storm that's not immediately overhead. There's something primal, perhaps, about the sound of thunder, something that speaks to our evolutionary history of seeking shelter from storms. Or maybe it's just the association with rain, with a temporary break from heat, with the drama and power of nature safely observed. Let your breathing slow to match the rhythm of distant thunder. Imagine yourself inside a safe shelter, hearing the rumbles roll across the sky, each one telling you about a lightning strike somewhere in the distance. The sound arrives, builds, fades away. Then another comes. It's the voice of the storm, the acoustic signature of those brilliant channels of plasma that briefly connect cloud and earth. Chapter 10. Different forms of lightning. The cloud-to-ground lightning we've been primarily discussing. The stepped leader descending, connecting to an upward leader from the ground, followed by a brilliant return stroke, is just one type of lightning. The atmosphere produces lightning in several different forms, each with its own characteristics, each telling us something about the conditions in which it forms. The most common type of lightning, actually, is cloud-to-cloud or intracloud lightning. These flashes occur entirely within clouds or between separate clouds, never reaching the ground. Scientists estimate that roughly 70% of all lightning is intracloud or cloud-to-cloud. From the ground, we see these as flashes that illuminate clouds from within, making them glow briefly, without any visible channel extending downward. Intracloud lightning typically occurs between the negative charge region in the middle of the cloud and the positive charge region at the top. Remember that tripolar structure we discussed? The positive and negative charge regions are separated by perhaps several kilometers of cloud, with electric fields between them strong enough to eventually trigger lightning. The process is similar to cloud-to-ground lightning. A leader propagates from one charge region toward another, though in this case it's moving through cloud rather than through clear air below the cloud. When the leader successfully bridges the gap between charge regions, a discharge occurs, neutralizing some of the separated charge. This discharge heats and illuminates the channel, creating the glow we see. Because the channel is embedded within the cloud, we don't see the detailed structure the way we do with cloud-to-ground strikes. Instead, we see the cloud light up, sometimes in sheets or widespread glows. This is sometimes called sheet lightning, though it's not fundamentally different from other forms. It's just intracloud lightning viewed through the obscuring bulk of the cloud itself. Intracloud lightning can also create sprites, but those are a separate phenomenon we'll discuss later. For now, let's continue with varieties of cloud-to-ground lightning. While most cloud-to-ground lightning is negative, meaning it transfers negative charge from the cloud to the ground, about 10% is positive lightning. Positive lightning originates from the positive charge region at the top of the cloud rather than the negative region in the middle. It typically strikes the ground further from the main body of the storm, sometimes appearing to come from clear or nearly clear sky. Positive lightning is often more powerful than negative lightning. The flashes tend to carry larger peak currents, transfer more charge, and last longer. A single stroke of positive lightning might transfer 100 coulombs or more, compared to the 5 or 10 coulombs typical of a negative stroke. The reasons for this difference aren't entirely understood, but it may relate to the typically greater distance the positive lightning has to traverse and the larger reservoir of positive charge available in the upper cloud regions. Positive lightning is also more likely to trigger wildfires, partly because of its greater energy and partly because it often strikes in regions away from the rain core of the storm, where vegetation is dry. There's some evidence that positive lightning is more common during the dissipating stage of thunderstorms, when the negative charge region has been partially depleted by previous lightning, but the positive region remains substantial. Another variant is ground-to-cloud lightning, also called upward lightning. This typically occurs from tall structures, towers, skyscrapers, mountain peaks, especially when strong electric fields exist above them. Unlike normal cloud-to-ground lightning where a downward leader from the cloud initiates the flash, in ground-to-cloud lightning, an upward leader from the tall structure initiates the flash. The conditions for ground-to-cloud lightning usually involve a particularly strong electric field at ground level, often in the presence of nearby cloud-to-ground strikes that have intensified local fields. The tall structure essentially reaches up into this strong field, and from its tip, an upward leader begins to propagate. This leader extends upward toward the cloud, potentially traveling several hundred meters or more. If the upward leader reaches a charge region in the cloud or connects with a downward leader coming from the cloud, a discharge occurs. Similar to ordinary lightning, ground-to-cloud lightning is less common than cloud-to-ground lightning overall, but it's the dominant form of lightning affecting very tall structures. The Eiffel Tower, for instance, is struck by lightning dozens of times per year, and most of these are upward flashes initiated from the tower itself. There's also ribbon lightning, though this is really just an optical effect rather than a different type of lightning. When strong winds are present and a multi-stroke lightning flash occurs. Each successive stroke may follow a slightly different path because the wind has blown the hot channel created by the previous stroke to a new location. From a distance, this can create the appearance of multiple parallel ribbons of lightning, all part of the same flash, but spatially separated by wind. Then there's bead lightning, a rare optical phenomenon where a lightning channel appears to break up into disconnected segments or beads shortly after the main flash. The physics of bead lightning isn't completely understood, but it may involve variation in the rate at which different segments of the channel cool and stop glowing. It's quite unusual and lasts only a fraction of a second. Forked lightning simply refers to the branching pattern that's common in cloud-to-ground lightning, where multiple branches of the stepped leader are illuminated during the return stroke. It's not a distinct type, but rather a description of appearance. Similarly, streak lightning just refers to the appearance of a single, relatively unbranched lightning channel. More exotic are the various forms of upper atmospheric lightning: sprites, blue jets, elves, and gigantic jets. These phenomena were only discovered relatively recently because they occur high above thunderstorms and are difficult to observe from the ground. Sprites are large, brief flashes that occur in the mesosphere, typically above particularly powerful positive lightning strikes. They appear reddish at high altitudes, fading to blue at lower altitudes, and have distinctive shapes often described as jellyfish-like or carrot-like. Sprites can extend from about 50 to 90 kilometers above the Earth's surface, much higher than the thunderstorms that trigger them. The mechanism behind sprites involves the intense electric field that briefly exists above a powerful positive lightning strike. This field can cause electrical breakdown in the thin air of the upper atmosphere, creating the luminous discharge we see as sprites. They last only a few milliseconds and are extremely large, sometimes 50 kilometers across. Blue jets are another form of upper atmospheric discharge. They propagate upward from the top of thunderstorm clouds at speeds of about 100 kilometers per second, forming narrow cones that extend up to about 40 or 50 kilometers in altitude. They appear blue due to emission from ionized nitrogen, and they're thought to be electrical discharges from the positive charge region at the cloud top. Elves are even more brief than sprites, lasting only about 1 millisecond. They appear as expanding rings of light, about 400 kilometers in diameter, in the ionosphere, roughly 90 kilometers up. Elves are caused by electromagnetic pulses from intense lightning strikes that propagate upward at the speed of light, temporarily ionizing the thin air where they pass. Gigantic jets are connections between thunderstorm tops and the ionosphere, essentially lightning that extends from the cloud top all the way up to altitudes of about 70 to 90 kilometers. They're extremely rare and were only documented photographically in 2002. Gigantic jets involve both the blue jet mechanism at lower altitudes and sprite-like discharges at higher altitudes. These upper atmospheric phenomena remind us that the electrical activity of thunderstorms doesn't stop at the cloud boundary. The enormous charges and fields in thunderstorms affect the atmosphere all the way up to the ionosphere and beyond. In fact, lightning generates electromagnetic waves that propagate around the world, creating what are called spherics, brief electromagnetic pulses that can be detected thousands of kilometers from the lightning strike. Lightning also produces X-rays and gamma rays. This was discovered only in the 1,980 seconds and 1,990 seconds, and was quite surprising. The mechanism involves runaway electron avalanches, where electrons are accelerated to such high energies that when they collide with atoms, they produce X-rays through a process called Bremsstrahlung radiation. Some lightning, particularly the initial stepped leader phase, produces brief but intense bursts of X-rays and gamma rays. There's even evidence of antimatter production in lightning. The gamma rays produced can interact with atomic nuclei to create electron-positron pairs, with the positron being the antiparticle of the electron. Most of these positrons quickly annihilate by encountering electrons, but their brief existence is another exotic aspect of lightning's physics. All of these varieties and associated phenomena emerge from the same basic process: charge separation in clouds, electric field buildup, and eventual electrical discharge. But the details of the charge distribution, the path the discharge takes, the intensity of the fields, and the atmospheric conditions at different altitudes all influence what exact form the lightning takes. The diversity of lightning types reminds us that nature rarely fits into simple categories. What we call lightning is really a family of related phenomena, all involving electrical discharge in the atmosphere, but expressing themselves differently depending on countless variables. Each thunderstorm is unique. Each lightning flash is unique. Each creates its own particular pattern of light and sound and electromagnetic radiation. You might find your attention drifting, your mind wandering from these descriptions of unusual lightning forms. That's perfectly fine. Let your thoughts flow where they will. The science will be here. These phenomena will continue to occur in storms around the world, and your understanding deepens even as you release the need to actively focus on every detail. Chapter 11. Lightning and Life on Earth. Lightning has shaped life on Earth in ways both obvious and subtle. Its effects extend from the microscopic scale of chemical reactions to the global scale of atmospheric composition. Understanding these effects helps us see lightning not just as a dramatic weather phenomenon, but as an integral part of Earth's systems. One of lightning's most important roles involves nitrogen fixation. Earth's atmosphere is about 78% nitrogen gas, N2. This molecular nitrogen is extremely stable. The two nitrogen atoms are held together by a triple bond, one of the strongest bonds in chemistry. This stability means nitrogen gas is unreactive under normal conditions. Most organisms, including plants, cannot use nitrogen gas directly. They need nitrogen in other forms, such as ammonia or nitrate. Nitrogen fixation is the process of converting nitrogen gas into these usable forms. Some bacteria can fix nitrogen biologically, using specialized enzymes. But lightning also fixes nitrogen through a purely chemical process. The extreme temperatures in a lightning channel, remember, 30,000 Kelvin or more, provide enough energy to break those strong triple bonds in nitrogen molecules. When nitrogen is split, the individual nitrogen atoms can react with oxygen in the air to form nitrogen oxides, particularly nitric oxide, NO. This nitric oxide can then react further to form nitrogen dioxide, NO2, which dissolves in rainwater to create nitric acid. This acid eventually falls to the ground, where it can be absorbed by soil and taken up by plants as a source of nitrogen. The amount of nitrogen fixed by lightning globally is substantial, though smaller than biological nitrogen fixation. Estimates suggest lightning fixes about 5 to 10 million tons of nitrogen per year. For comparison, biological nitrogen fixation accounts for about 100 million tons per year, and human industrial nitrogen fixation for fertilizer production is also about 100 million tons per year. But before humans began industrial nitrogen fixation about a century ago, lightning and biological processes were the only sources of fixed nitrogen. Over Earth's history, lightning has been continually supplying fixed nitrogen to ecosystems, enabling plant growth in regions where nitrogen-fixing bacteria might be less active. Some scientists have even speculated that lightning-fixed nitrogen may have been important for the origin of life, providing a source of nitrogen compounds needed for early biochemistry. Lightning also plays a role in atmospheric chemistry more broadly. The nitrogen oxides produced by lightning are involved in ozone chemistry. In the presence of sunlight and other atmospheric gases, nitrogen oxides can both produce and destroy ozone, depending on altitude and other conditions. The ozone layer in the stratosphere, which protects Earth's surface from harmful ultraviolet radiation, is influenced by the nitrogen oxides that originate partly from lightning. Lightning produces other chemical species too. The intense energy in the lightning channel can create ozone directly. It can break apart molecules of carbon dioxide, water vapor, and methane, creating a variety of reactive fragments. Some of these reactions produce compounds that wouldn't form otherwise, contributing to the complex chemistry of the atmosphere. Another important role of lightning is in the global electrical circuit. Earth and its atmosphere together form a giant capacitor, with a voltage difference of about 300,000 volts between the ground and the ionosphere, about 50 kilometers up. This potential difference is maintained by thunderstorms, which act like batteries charging the capacitor. Here's how it works. In fair weather regions, away from storms, there's a small current constantly flowing downward through the atmosphere, from the ionosphere to the ground. This fair weather current is only about 1,000 amperes globally, but it's constantly discharging the atmospheric capacitor. If this were the only process occurring, the Earth atmosphere voltage would decay away in about 10 minutes. But thunderstorms pump charge back up, maintaining the voltage. When lightning transfers negative charge from clouds to ground, it also, through various mechanisms, transfers positive charge upward to the ionosphere. The net effect is that thunderstorms act as generators, pumping current upward in storm regions to compensate for the downward current in fair weather regions. At any given moment, there are about 2,000 thunderstorms active somewhere on Earth, providing about 2,000 lightning flashes per second globally, and these maintain the global electrical circuit. This global circuit may have biological effects. Some researchers have investigated whether the atmospheric electric field affects biological processes, from seed germination to animal behavior. The evidence is mixed, and it's difficult to separate effects of the electric field from effects of other environmental variables. But it's an area of ongoing research, and it's possible that life on Earth has adapted in ways that respond to or utilize the ever-present atmospheric electric field. Lightning also has more direct effects on ecosystems through fire. Lightning is a major cause of wildfires, particularly in regions with dry seasons. A lightning strike can ignite a tree, dry grass, or other vegetation, starting fires that can spread over large areas. While fires are often thought of as destructive, they're actually an important part of many ecosystems. Some plants have evolved to depend on fire. Certain pine species have cones that only open and release seeds after being exposed to the high temperatures of a fire. Some grassland species are adapted to regular burning, which clears away dead material and provides nutrients from ash. In these ecosystems, lightning-caused fires are part of the natural cycle that maintains ecosystem health. Of course, fires can also be destructive to human property and sometimes to ecosystems, especially when fuels have built up due to fire suppression policies. But from a purely ecological perspective, lightning fires have been shaping landscapes for millions of years, long before human fire suppression, and many ecosystems are adapted to regular burning. Lightning strikes can directly affect individual organisms too. Trees struck by lightning sometimes survive, though with visible damage, a strip of bark blown off or a split trunk. Other times, the tree is killed outright, either by the electrical current or by the explosive vaporization of water inside the tree that can blow it apart. In a forest, lightning-struck trees create small clearings that can be colonized by sun-loving species, adding to habitat diversity. Animals can be killed by lightning strikes, though this is relatively rare. When it does happen, it's often because the animal was touching or near an object that was struck. Current flowing through the ground from a lightning strike can also affect animals standing nearby. This is why it's dangerous to stand near a tree that's been struck, even if you're not touching the tree directly. The current spreads out through the ground, and the voltage difference between your feet, the step potential, can be enough to drive a dangerous current through your body. For humans, lightning is one of the most dangerous weather phenomena. Globally, lightning kills thousands of people per year and injures many more. In the United States alone, lightning causes an average of about 20 to 30 deaths per year. Many of these could be prevented with proper precautions: seeking shelter when thunder is heard, avoiding open fields and tall, isolated objects during storms, not using landline phones, or touching plumbing during storms. Modern buildings with proper grounding and lightning protection systems can provide excellent safety from lightning strikes. The key is to provide a low-resistance path for the lightning current to flow to ground without passing through the building's structure or interior. Metal frames, proper grounding rods, and lightning rods can all contribute to effective lightning protection. Despite its dangers, lightning has also captivated human imagination throughout history. Many cultures have associated lightning with gods or supernatural powers: Zeus throwing thunderbolts, Thor wielding his hammer, indigenous Australian rainbow serpents. This is understandable given lightning's dramatic appearance and power. It's only relatively recently, within the last few centuries, that we've come to understand lightning as a natural electrical phenomenon rather than a supernatural one. Benjamin Franklin's experiments in the mid-1700s, particularly his famous kite experiment, helped establish that lightning is electricity. This was a profound insight, connecting the dramatic celestial phenomenon of lightning with the small-scale sparks and shocks that people had experienced in laboratory settings. It opened the way for understanding lightning scientifically and for developing protection systems based on that understanding. Today, lightning research continues. Scientists fly instrumented aircraft through thunderstorms, launch rockets that trigger lightning, use high-speed cameras to capture the detailed progression of lightning, and employ lightning detection networks to track strikes globally. There's still much we don't fully understand: the exact mechanisms of lightning initiation, the reasons for the variety of lightning types, the details of how lightning interacts with the global electrical circuit. But we know far more than Franklin did, and our knowledge continues to grow. Each new study adds to our understanding. Each observation refines our models. Each measurement constrains the parameters in our simulations. Lightning, once mysterious and attributed to divine action, is now seen as a consequence of physical laws. Complex, certainly, difficult to predict in detail, yes, but ultimately understandable within our scientific framework. And perhaps there's still wonder in that. Understanding lightning doesn't make it less impressive. If anything, knowing the process by which invisible collisions between ice crystals ultimately produce channels of plasma hotter than the sun makes lightning even more remarkable. Nature needs no supernatural explanation to be amazing. Chapter 12. Standing Beneath the Storm. We've come a long way in our understanding, from water droplets evaporating from the ocean to the brilliant flash that illuminates the sky. Let's take these final minutes to reflect on what we've learned and to place it in a broader context. Lightning is, at its heart, a story about imbalance, seeking balance. The charge separation in the cloud creates an electrical imbalance, with positive charges in one region and negative charges in another. This imbalance creates tension, stored energy, waiting to be released. The atmosphere's insulating properties keep this imbalance in place for a time. But eventually, the tension becomes too great. The air breaks down, a conducting channel forms, and current flows until the charges are partially neutralized. This pattern of imbalance and restoration of balance is common throughout nature. A ball rolled up a hill wants to roll back down. Water behind a dam wants to flow downhill. Heat flows from hot objects to cold ones. In each case, the system has been pushed away from its lowest energy state, and it naturally tends back toward that state, releasing energy in the process. Lightning is the atmosphere's way of releasing the electrical potential energy that builds up through the mechanical process of charge separation in clouds. The energy ultimately comes from the sun. It's solar heating that drives convection, that lifts moist air to form clouds, that powers the updrafts that allow charge separation to occur. Lightning is one way that solar energy, temporarily stored as electrical potential energy, gets released back into heat and sound and light. From a certain perspective, lightning is inefficient. Most of the energy goes into heating air and producing sound, forms of energy that quickly dissipate and disperse. Very little of the energy does useful work in the traditional sense. And yet, efficiency isn't really the right framework for evaluating natural processes. Nature isn't trying to accomplish tasks efficiently. It's simply following physical laws. And lightning is what those laws produce, given the conditions in thunderstorms. If you were to watch a thunderstorm from a safe distance, knowing what you now know about the processes occurring within it, you might see it differently. The dark clouds aren't just water droplets and ice crystals. They're dynamic systems where billions of particles are colliding, where updrafts and downdrafts are moving air at speeds that would challenge the strongest winds you've experienced on the ground, where electric fields are building to extraordinary strengths. The lightning you see isn't just a bright flash, but the culmination of all those invisible processes. It's the moment when the stepped leader, having descended incrementally from the cloud, finally connects to ground. It's the instant when current measured in tens of thousands of amperes suddenly flows through a channel no wider than your arm. It's the brief time, 100 microseconds, when a column of air becomes hotter than the surface of the sun. And the thunder you hear is the acoustic signature of that heating, the sound of air being explosively expanded by the sudden injection of enormous energy. It tells you about the shape of the lightning channel, about your distance from the strike, about how sound propagates through the atmosphere on this particular day. There's a kind of poetry in all of this. Though it's a poetry written in the language of physics, the equations that describe charge separation, electric field buildup, and electrical breakdown are as elegantly structured as any verse. The patterns that emerge, the branching of the stepped leader, the flickering of multi-stroke flashes, the rolling rumble of thunder, have an aesthetic quality that transcends their purely physical nature. Perhaps this is part of why science can be so satisfying. When we understand how something works, when we can trace the chain of causation from simple processes to complex results, when we can see the underlying unity behind diverse phenomena, there's a deep pleasure in that understanding. It's not the same as the initial wonder we might feel seeing lightning for the first time, but it's no less valuable. Understanding and wonder can coexist, each enriching the other. You might imagine yourself standing beneath a thunderstorm in some safe location, perhaps watching from a covered porch as the storm passes overhead. You see the clouds illuminated from within by intracloud lightning. You see the brilliant forked channels of cloud-to-ground strikes. You hear the immediate crack of close thunder and the distant rumble of far-off strikes. And now, you understand what you're witnessing. You know that inside those clouds, ice and graupel are colliding, charge is being separated, electric fields are building. You know that each lightning flash begins with an invisible stepped leader descending from the cloud in discrete jumps, each step extending the ionized channel closer to ground. You know that when connection is made, the return stroke races upward at 1/3 the speed of light, heating the channel to temperatures that would vaporize any material object. You know that the thunder is the sound of that heating, that it rumbles because you're hearing sound from different distances arriving at different times, that its character is shaped by the atmospheric conditions through which it propagates. You know that the lightning is fixing nitrogen, contributing to the global electrical circuit, perhaps igniting fires that will shape the landscape. All of this knowledge sits with you as you watch the storm, not diminishing the experience but enriching it. The lightning is no less beautiful for being understood. If anything, it's more beautiful, because you can appreciate not just the visual spectacle but the elegant physics that produces it. As you continue to rest, perhaps drifting towards sleep, let these ideas settle in your mind. The processes that create lightning are the same processes that have been occurring for millions of years, long before humans existed to witness them. They'll continue long after we're gone. Lightning is part of the planet's natural functioning, as regular and predictable in aggregate as ocean waves or volcanic eruptions, even though each individual lightning strike is unique. The thunderstorms happening right now, somewhere on Earth, and there are always thunderstorms happening somewhere, are following these same patterns. Charge is being separated, fields are building, leaders are propagating. Return strokes are heating channels to extreme temperatures. Thunder is rolling across landscapes, and all of it emerges from the simple fact that water exists in multiple phases, that ice and liquid water have different electrical properties, that particles collide in updrafts, that air can be ionized. From small causes, large effects, from simple rules, complex patterns. From ice crystals, no bigger than a grain of sand, lightning bolts that stretch across kilometers of sky. This is the nature of emergent phenomena. Systems where interactions at one scale produce behaviors at a completely different scale. Behaviors that couldn't have been predicted from knowing the component parts alone. Lightning is one of the most accessible examples of this kind of emergence. We can understand the components: water molecules, ice crystals, electric fields, ionization processes. We can describe the intermediate steps: charge separation, leader propagation, return strokes, and we can observe the final result: the bright flash, the thunder, the effects on the atmosphere and landscape. Each level of organization has its own logic, its own patterns, and they all fit together into a coherent whole. As you settle deeper into rest, as your breathing slows and your thoughts become less directed, the storm continues in your imagination. Or perhaps it's real. Perhaps you hear actual rain falling or actual thunder rolling in the distance. Either way, the storm is a reminder of the power and beauty of natural processes, of the fact that the universe operates according to laws we can understand, of the endless fascination available in studying how the world works. Lightning, born from ice and air and sunlight, shaped by physics and chemistry and the geometry of clouds, manifesting as brilliant light and rolling sound and fixed nitrogen and global electrical currents. It's all connected, all part of Earth's systems, all ultimately deriving from the energy the sun pours onto our planet every day. Rest now, knowing that somewhere, perhaps many places, lightning is flashing at this very moment. Charge built up through countless tiny collisions is being released in brilliant bursts. Leaders are stepping down through thunderclouds. Return strokes are racing upward through ionized channels. And the ancient dance continues, as it has for all of Earth's history, following the unchanging laws of nature with mathematical precision and wild, unpredictable beauty. Sweet dreams. And may your rest be as peaceful as the calm after a storm. When the lightning has moved on, the thunder has faded, and only the gentle sound of rain remains.